Okay, so let's go up to number 4. I think that'll be it for me for today. That's a lot of them today. Might do another one in an hour or so, but let's see how we can do on trig proofs. That's everybody's favorite topic, right? It's been a minute since we've done those. So let's see what happens when we try to do some proving. So we had a variety of strategies. This is definitely one of those problems that it helps sometimes to go back. So I'm actually going to go a little bit out of order and start with number 25, because this one just to me looks a little bit more simple and straightforward to start with. So one of the strategies that we learn when you look at a big mess of things is just to turn things into sines and cosines if you don't really know what you're going to do. So we had to decide which side looks worse, left or right. And I don't think there's any debate here that the left side looks more obnoxious than the right side. So that's the one we're going to play with. So I'm going to start with this cotangent here, and I'm going to rewrite the cotangent as a cosine over sine. So one thing that I did tell you guys to do is you always start every problem as if you do one thing at a time. And so the one thing that I chose to do is turn everybody into sines and cosines. Now on the next step, I can either do some algebraic simplification, like cross things out. I could substitute in something for something else, like I could take sine squared plus cosine squared and call it 1. Or some such. This problem, I think we can very quickly tell that if I could cancel those two things out, that would be pretty good because those would cancel. Now, I have 1 over sine in the first one. I have a 1 over sine in the second one. And that works out quite well for us because remember, my goal is to show that that is cosecant squared. Now, I'm going to do a little simplification here because I know that 1 over sine is in fact a cosecant. 1 over sine is also cosecant. So I'm just doing a simple substitution of writing what it is. And my goal is just one line at a time to prove and show that this answer simplifies to the answer that was given. And clearly a cosecant times a cosecant is a cosecant squared theta. And remember, our final step should be what we call reflexive, where a equals a, the two values are the same. And then we put a little box down at the bottom saying, hey, I like what I did, I'm feeling comfy. Now, this one was pretty easy. There might be a problem on the final that has that kind of flavor where if you just set it up, things cancel out and it just comes out nice and pretty. But, you know, we've done problems like this too, where there's some other little tricks up our sleeve, which were called Pythagorean identities. One of those Pythagorean identities is that sine squared plus cosine squared is 1. There's another one, which is if you divided each of these things above by the cosine, you'd get tangent squared plus 1 equals secant squared. And last but not least, if I divided all of these by a sine, I'd get 1 plus cotangent squared equals the cosecant squared. This turns out to be pretty helpful. So what we're going to do is we'll look at 24, and just so I can show it once, this time instead of modifying the left side to look like the right, I'm going to modify the right to look like the left. So there's a couple of ways to view this problem, but one of my favorite ways to look at it is to multiply by what we call a conjugate. So I saw that 1 minus sine, and I decided, this 1 plus sine, I decided to multiply the top and bottom by 1 minus. Now keep in mind, I'm not going to touch the left side at all. So what I'm going to do is I'm going to have the cosine of theta times 1 minus sine. And I want you to notice something that is very, very convenient. My goal is to make it look like this thing over here. And I already have something that I want on top. But if you multiply this on the bottom, you get 1 minus the sine squared. Again, if you just distribute 1 plus sine times 1 minus sine, you get 1 minus sine squared, which is pretty nice. Now again, I'm going to leave the numerator alone because I actually have something sitting right here that I really, really want to have there. So I'm hoping that that's going to stay put and it's going to be part of the answer that I have in the long run. But something really, really nice happened right here, because if you look at this identity, 1 take away the sine squared, if you move this to the other side, you can see how 1 minus sine squared is in fact cosine squared. And that's actually a very good thing because you'll notice, change colors, I wanted a cosine in the bottom, and now I have that. So the only thing I would have left to do to complete my journey is notice that if I took the cosine on top and the cosine on the bottom and I canceled them, I'd have a single cosine left on the bottom. And I still have that 1 minus the sign that is left on top. And notice that I have exactly what I wanted on top, and I have exactly what I wanted on the bottom, and we're done. And so again, like I said, we could either write the little box thing, or if we wanted to, we could write QED, which stands for it has been demonstrated, in a fancy Latin format. Okay, now moving on to not exactly a proof, but something that has some real similarities to it. We're going to find out when those things are equal. So in our list of formulas that we have back in the time, we had some double angles and double angle identities. I need to kind of bring that out over here. I have them written on this card right here. So you'll notice that anytime you see a double angle identity, we have a substitutor that we could put into place. So I'm going to take this sine of 2 theta and rewrite it as 2 sine theta cosine theta. And I want to know, when is that little set of data true, okay? Now, in most math classes, you've been trained that when we have an equation, we really like things to be set equal to 0. It just makes life much, much simpler. So we're going to go ahead and move this cosine across to the other side, because if I can move it to the other side, then I would notice that I have a common factor. So what I'm going to do is I'm going to take a cosine out of both of those. And that should leave me with 2 sines out of here, because I took the cosine out and I took this cosine out, which is going to leave the number 1. So notice that I removed the cosine that they had in common, put it out here in front. And so the only thing left to do is, the only way that this product can be 0 is if the cosine itself is 0, or if the sine itself is negative 1/2. And now we're back to a little quick unit circle story. And I happen to know that the cosine would be 0. Again, we could go back to the first page of our review. And I know that the cosine is only 0 right here at pi over 2. So sorry about flipping pages back and forth, but I didn't really want to redevelop that thing. So I could pick pi over 2, which is straight up, and 3 pi over 2, which is straight down. And the sine is negative in these 2 quadrants. And I'm looking for some kind of a pi over 6, because the sine of pi over 6 is 1/2. But I needed the 2 that were negative. And so I needed to go 6 pi over 6 plus a little more. So 7 pi over 6 would achieve the 3rd quadrant. And 11 pi over 6 would make it almost the whole way around the circle, because this would be 12 pi over 6. So those are good answers. Now, keep in mind, you could actually do a little bit of this on a calculator. So I am going to take the time to look at it in this way. You'll notice that we could come in here and we could type in what we have been given, which is the sine of 2 theta and the negative cosine of theta. I'm going to make my window go from 0 to 2 pi, because there's an infinite number of answers, but we don't want to write them all down. We just want to write down some of those answers.
Maybe.
Okay, you're on video. Bye. And then we're looking at from negative 1 to 1, because that's what a sine and cosine would do. Okay, so I'm going to look at that graph, and according to my estimate, it looks like I have 4 answers, and it looks like when I do this graph, there's 1, 2, 3, and 4 answers. And so we could just go and find a couple, but second calculate, let's find the intersection, number 5. I move the cursor kind of close to one of the intersections. Enter, enter, enter. And I got 1.57. Now, what you'll notice is 1.57 is this kind of weird number, but let's check out what is pi over 2. That's 1.57. So this answer was that first point of intersection, and we could check all those answers pretty well. All right, moving to number 27. We'll try to go through this a little bit more quickly than that first one. We'll overanalyze. I do unfortunately have 3 potential candidates for a substitution in here. I could use cosine squared minus sine squared, 1 minus 2 sine squared, or 2 cosine squared minus 1. And I'm going to pick this one right here because it's referring to a sine which matches what the problem has. So let's do that. Let's rewrite this as 1 minus 2 sine squareds. Let's leave this as a sine. Now, again, like I said, I'd like to make it equal to 0, so I'm going to move the sine squared over. I'm going to leave this sign where it is, and I'm going to move that 1 over. And then I'm going to do just a little ax squared plus bx plus c, little quadratic. Some of you guys like to do diamond problems. I personally prefer guess and check because I know the only way that I can get 2 sine squareds is 2 sines times sine. The only way I can get the number 1 is by putting a couple of 1s, and then I just have to decide if I'm going to get a positive or a negative. So what I do is I look at the outer and the inner terms, and I see a 2 sine and a 1 sine. How can I get a negative out of a 2 and a 1 would only be if the 2 part was negative and the 1 part was positive. So again, zero product property says the only way that this could be true is if the sign itself was 1, which happens at pi over 2. Again, unit circle, you can look through that thing. Or if the sign is negative 1/2, and you'll notice that was kind of nice. That's the same answer that we have over here. So I'm not going to redevelop that idea. I'm just going to chronicle it right there. So, so keep in mind, I can graph that if I want to. You're fine, Lindsay. I can graph that if I want to and show that there's actually 3 answers, but you don't have to. So my last one is down here, number 28, and then we're going to be done with this. I'm going to use, my friend, the Pythagorean identity that we had earlier. I have it listed up here at the top. See how sine squared plus cosine squared is 1? I'm going to choose to replace cosine squared with 1 minus sine squared, because now I don't have multiple trig ideas. We just have one of them, just sine, that's it. So a little bit of work. Now I'm going to move everything over and set it to one side. So if I brought the 2 sine squared to the left, it's going to go this way. I'm going to leave that sign where it is. And when I bring the 1 across, I'd be looking at this. And now that looks really, really close to the problem that I had right here. The only problem was, unlike this problem that had a minus on the sign, this one has a plus. Darn it, so close. So its factors are going to be almost the same as we just had. It's just going to flip which one is positive and which one is negative. So that means if I want the sign to be -1 or the sign to be 1/2, we are almost there, because this only happens at 3 pi over 2. Again, the reason why is because if the sign is negative, it has to be straight down. Or if the sign is positive, it has to be in 1 or 2. All students take calculus. So the 2 pi over 6 answers that are attached to the idea of the sign being 1/2 of pi over 6. So I got 1 pi over 6, we got 5 pi over 6, and hey, we are now halfway done with the review. I will see you back in class. Bye-bye.